For thousands of years, our relationship with fire has been one of survival and containment. At its simplest level, fire is a chemical reaction, the rapid oxidation of a fuel source that releases light and heat. To stop it, we have traditionally relied on the fire triangle, removing either the heat, the fuel, or the oxygen. Water has been our primary tool because of its remarkable ability to absorb heat. When water touches a flame, it undergoes a phase change into steam, absorbing a massive amount of thermal energy in the process, effectively chilling the fuel below its ignition point. In ancient Rome, firefighting was a matter of organized manpower rather than sophisticated machinery. The vigiles, Rome's first professional firefighting force, utilized a system known as the bucket brigade. Hundreds of men would stand in a line, passing buckets of water from a stone aqueduct to the site of the fire. They also employed siphos, which were basic hand pumps made of bronze. While innovative for the time, these devices lacked the pressure to reach upper floors, forcing the vigiles to rely on axes to tear down neighboring buildings to create fire breaks. The next major leap didn't occur until the 17th century, spurred by the devastating Great Fire of London. Engineers began designing larger, carriage-mounted manual pumps. These machines required dozens of people to pump long wooden handles up and down to build pressure. Leather hoses, stitched together like shoes, finally allowed firefighters to direct water from the street into the heart of a building. However, these hoses often leaked or burst under pressure, and the physical exhaustion of the crew meant that large fires were still almost impossible to stop once they took hold. The Industrial Revolution replaced human muscle with the power of steam. By the mid-1800s, horse-drawn steam fire engines could pump hundreds of gallons of water per minute at high pressure, far exceeding the capabilities of any manual crew. These massive boilers were kept preheated so they could reach operational pressure quickly upon arrival. While powerful, these machines highlighted a growing problem. The more water we use, the more damage we cause. In many cases, the weight of the water used to extinguish the fire caused the building structure to collapse, destroying what the flames had spared. To solve the problem of water damage, scientists looked toward chemistry. In the mid-20th century, aqueous film-forming foams, or AF, were developed. Unlike water, which can run off a surface or sink into it, these foams are designed to float on top of liquid fuels. At a molecular level, the foam reduces the surface tension of the water, allowing it to spread rapidly across a fire. It creates a physical barrier that cuts off the oxygen supply and prevents flammable vapors from escaping, making it far more efficient than water for industrial and chemical fires. In environments where even a drop of foam or water could be catastrophic, such as data centers or museums, we use gaseous suppression systems. These systems flood a room with inert gases like argon or CO2, or chemical agents that interfere with the fire's chemical chain reaction at a molecular level. By rapidly lowering the oxygen concentration or absorbing the heat within the air itself, the fire is extinguished in seconds. The hardware remains dry and undamaged, allowing sensitive electronics to continue functioning throughout the entire process without a single short circuit. As we move into the 21st century, the focus is shifting toward autonomous intervention. In high-rise buildings where traditional ladders cannot reach, researchers are deploying AI-driven drone swarms. These drones use thermal imaging and lidar to navigate through thick smoke and intense heat, identifying the exact seat of a fire. They can then deploy concentrated bursts of suppression chemicals or localized water mists. By operating in swarms, they can surround a fire from multiple angles, providing real-time data to human commanders while keeping firefighters out of the most dangerous zones. Perhaps the most counterintuitive development is the use of sound to fight fire. A sonic extinguisher uses low-frequency acoustic waves, essentially a deep bass hum, to vibrate the air around a flame. These sound waves increase the velocity of the air, thinning the boundary layer where the combustion occurs. This disrupts the flame's ability to pull in oxygen and stay attached to the fuel source. It literally blows the fire out using nothing but air movement. This technology offers a future where fires can be extinguished with zero cleanup and zero chemical footprint. The evolution of firefighting is moving away from the blunt force of the bucket brigade and toward the precision of physics and computer science. We are learning that the best way to fight a fire isn't necessarily to drown it. but to understand its mechanics so well that we can dismantle the reaction with surgical accuracy. From ancient bronze pumps to autonomous drones and sound waves, our engineering war against fire has become less about water and more about the clever manipulation of the very elements that allow fire to exist in the first place.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.